So thanks very much for the invitation. It's a pleasure to give this mini course on Igusa stacks together with Mingjia. So to save myself some time, I've written just the notation from Mingjia's talk. So we're going to start with some Shimura datum of Hodge type, GX. But really, you should take it to be kind of your favorite Shimura variety, because what it is precisely won't matter very much for this talk. So if you're most comfortable with the case of the modular curve, then you should just take it to be the modular curve. So you could take G to be GL2 over Q. Or, whatever PEL type, or, you could think about that eventually these results should also be available in the abelian type case. So mu is the Hodge co-character. It's a minuscule co-character of G. I should have said maybe that G is the base change to QP of this fancy G that's over Q. This is the reflex field, the field of definition of the conjugacy class of the Hodge co-character. And we're going to pick a rational prime P and then a prime of the reflex field above it. And we're going to work over this p-adic field that I call E. And we're going to look at all our Shimura varieties as diamonds. So we want to take the Shimura variety defined over the reflex field, base change it to E, and look at the associated diamond. This is the case of finite level, and this is for some just infinite level, so just some tame level away from P that's fixed, and that's not going to matter for this talk. And another thing is that I want to assume for this talk that the Shimura varieties are all compact. So this talk is about kind of cohomological applications of the Igusa stack diagram. And for now, I just want to restrict to the case where these are all compact. And then you can ask in the next talk. So in the last talk that I give, which is talk 4, I'm going to discuss kind of the non-compact case, and I'm going to say something about that. All right, so we have the Igusa stack diagram. So the Shimura variety with infinite level at P going to a flag variety that Mingjia denoted as FL mu inverse. And so this should really be, again, the analytification of a flag variety. So I take the associated diamond. This is the Hodge-Tate period morphism. There's the Beauville-Laszlo map that goes to Bunji. And then the Igusa stack completes this to a Cartesian diagram. Okay, so the Igusa stack, again, with some tame level. All right, and this is the map that Mingjia denoted, pi bar Hodge-Tate. Right. Maybe I want to make kind of 2 more comments about the geometry. So one is that I could have drawn a Cartesian diagram on top as well by taking the fiber product of the Shimura variety over the Igusa stack with the Shimura variety. And that would be the same as taking the fiber product of the Shimura variety over Bunji with the flag variety. If I restrict to a particular Newton stratum, this recovers the Mantovan product formula in the way that was proved in my joint work with Schulze. And in turn, this relies on, work of Oort, Mantovan, and Harris-Taylor, who studied geometry of the special fibers of Shimura varieties. And then if I restrict particularly to the basic point over which this Igusa stack lives, then that recovers Rappaport-Zink uniformization. So this diagram really encapsulates a lot of what was known about the geometry of Shimura varieties beforehand. And so that's kind of one thing that makes it great. And another thing that makes it great is just there are a lot of cohomological consequences that you can derive from it. And the other comment I wanted to make, just to remind people from Mingjia's talk, so this parameterizes a line bundle inside 2 copies of the structure sheaf. But you can view this as a modification, maybe I'll say, you can view this as a modification of the trivial G bundle on the Fargues-Fontaine curve. In other words, it turns out you can identify this with a Schubert cell inside the B-de-Rham affine Grassmannian, B-de-Rham plus affine Grassmannian, and this is what ultimately, this identification is what gives you this Bovie-Laszlo map. And just to say so, this embeds into the whole B-de-Rham plus affine Grassmannian. So this is here is a minuscule Schubert cell. And what makes this identification possible is the fact that the Hodge co-character was minuscule to begin with, which follows from the axioms of having a Shimura datum. Right, so there's kind of two ways of viewing this space, just as a flag variety in a very kind of classical way, and then you analytify it, but it also has this interpretation of parametrizing modifications of the trivial G bundle on the Fargues-Fontaine curve with poles bounded by mu inverse. And this is something that is going to be used later in this talk. Okay, so as I said, this talk is supposed to be about cohomological consequences. So we want to understand, so maybe this is, yeah, already two cohomological consequences. We want to understand the cohomology of the Shimura variety. In this talk, I'm going to work with some ring of coefficients lambda, which I'm going to say is some O mod some uniformizer, but with residue characteristic L different from P. So this is a talk really about L not equal to P. And for technical reasons, it's going to be actually simpler for me to work in this torsion case, but consequences for the cohomology of Shimura variety with characteristic zero coefficients you will recover by taking limits. All right, so these are my coefficients, and we want to understand the cohomology of the Shimura variety, say with infinite level at P, base change to E bar, and then with coefficients in lambda. And so it's compact, so usual cohomology is fine. And this can be identified with a co-limit over the levels at P of the finite level Shimura variety. Okay, so this has some structures. It has an action of a Hecke algebra away from P. Right, so product of spherical Hecke algebras at all but finitely many primes. It has an action of GQP, and it's a smooth representation of GQP. You can recover any finite level by taking invariance under the corresponding compact open subgroup. And it also has an action of the Weil group of E. And ideally, we would want to understand this cohomology with all its structures in terms of this diagram. So essentially, in terms of the relative cohomology of the Igusa stack. Right, so the idea is to kind of break up the computation of the cohomology of Shimura varieties in two steps. Namely, push forward to the flag variety and then take total cohomology. But the push forward to the flag variety, because this diagram is Cartesian, will just be pulled back from the relative cohomology of the Igusa stack. So I'll write down the precise theorem. So but just to say, F here is going to be my notation for the relative cohomology of the Igusa stack with lambda coefficients. And, well, this is turns out to be a sheaf on Bungie. In fact, lives in this category of sheaves defined by Fargues-Schulze. And it also has, an action of the Hecke algebra away from P. All right. But you don't see these structures directly on the relative cohomology of the Igusa stack. And So the theorem, I think, maybe just to say, because the Igusa stack is really, I mean, morally, we would like to have an Igusa stack that lives over all of Bunge. But the way that it's constructed from this moduli theoretic definition that Mingjia gave yesterday, it really only lives over a minuscule part of Bunge, right? So here, I could have restricted to the locus of Bunge that's less than or equal to mu inverse. And so for this reason, f is really only supported on this. So that's just one comment, that in an ideal world, we would like a sheaf on the whole Bunge, but really, somehow, I think actually maybe Daniel Kim used, like this is kind of the observable Igusa stack. And so I guess this is the observable part of its cohomology. All right. And so here's the theorem. And so I wasn't completely sure who to attribute it to, but so let me just say a stratified version of this theorem is in the work of Hamann and Lee, and then kind of the version that really works over the Igusa stack, so not over individual Newton strata, but over the whole observable Igusa stack, is due to Daniels-van-Hoften, Kim and Zhang. And this theorem says, sorry, I mean, I know it, but just so that I don't forget any of the structures. So there is an H away from P cross GQP cross WE equivariant isomorphism between the cohomology of the Shimura variety with infinite level at P and the following thing. So you take the relative cohomology of the Igusa stack. That's my sheaf curly F. And then you shift it by the dimension of, kind of shift it so that it's in degree D, by the dimension of the Shimura variety D. And there's a Tate twist. And to really make this, I should have chosen some square root of P in here to make sense of that. So lambda should be taken to be big enough. All right, and then what you do is you apply a Hecke operator, a geometric Hecke operator in the sense of Fargues and Schulze to this object. And then you take restriction to the neutral point of Bunge. Okay, so this is the formula. And for the first part of the talk, I just want to explain to you why this formula is true. So really like looking at various base change morphisms carefully. But let me just say that this formula breaks up the cohomology of the Shimura variety, which is a global object, into this piece F, which also has global information because it has this action of the Hecke algebra away from P. And for example, because we know that its fibers are Igusa varieties and their cohomology sees automorphic representations of G. So this is global. Although, again, kind of this is the observable part that's only defined over p-adic field, whereas the Shimura variety is defined over Q. But still, the systems of Hecke eigenvalues in it come from automorphic representations, and then this is local. Right? So just like the geometric diagram breaks things up into this side that's purely local and this part that's global, so you get the same thing for the cohomology of the Shimura variety. And so this has potentially very powerful consequences. And I'll talk about consequences in a second, but I have to tell you what these things are more precisely. So as I said, D is the dimension of the Shimura variety, and it's the same as the dimension of the flag variety. Let's see, I1 has also shown up in talks this morning. So this is the open immersion of the neutral point of Bun-G into Bun-G. And remember that Fargues-Schulze showed that this can be identified, well, with a classifying stack in general of some group GB tilde, but when B is just the identity, when B is just 1, the group GB tilde is just GQP. And so you can identify it like this. And then we have an equivalence of categories right, due to Fargues-Schulze again, between the derived category of smooth representations of GQP with lambda coefficients and the category of sheaves on this neutral point. Right, and this identification is really used. So a priori, this is, you can think of as just a sheaf on the neutral point, but using this identification, you can view it as a smooth representation of GQP, and this isomorphism uses this. So I've kind of written it quickly, and there's a bit of an abusive notation here. Okay, so that's that. And then the most interesting part is T mu, which is a geometric Hecke operator, as constructed by Fargues and Schulze. And I'll tell you precisely what this is. So in general, what they have is they have a Hecke stack with two different maps to Bun-G. And in fact, one of these maps is to Bun-G cross div1, which is the mirror curve. So this is spa-D of E breve mod the lift of Frobenius to the Z, so-called mirror curve. All right, let me say this is P1 and this is P2. So for some perfectoid space, maybe I just want to work over FP bar. This parameterizes. So this is the groupoid of an untilt and then modification of G bundles on the Fargues-Fontaine curve. X, say, Fargues-Fontaine S, and it's a meromorphic modification, so it's a map that's defined outside this closed Cartier divisor of degree 1, S sharp, and it's with poles bounded by mu. Okay, and so the map to div 1, it remembers the Cartier the closed Cartier divisor of degree 1. The map, so to Bun-G here is taking it to E2, and the map to Bun-G here is taking it to E1. All right, so the formula for the Hecke operator is if I have G, a sheaf in this category, so sheaf on Bun-G, in this category defined by Fargues and Schulze, then T mu of G is you take P1 upper star of G, you tensor it with some Satake sheaf, so the derived tensor product over lambda. This Satake sheaf knows about the co-character, and this definition works for general co-characters. They don't need to be minuscule. And then there's a P2 lower star, right? So where S mu is the Satake sheaf associated to, so you view mu as a character of the Langlands dual group, and you can form a representation of the L group of G from it. And this has a sheaf associated to it under geometric Satake. And so the square root of p that I chose up there is used to normalize the geometric Satake correspondence. And in this particular case, where mu is minuscule, so in general, these are defined as some middle extensions from open Schubert cells. But in the case, so because our mu is minuscule, this geometric Satake sheaf has a nice form. S mu is just lambda with a shift in dimension by d and a Tate twist by d over 2. Okay, so d was this dimension, and you see this shows up here. You should think essentially that somehow what this diagram does is doesn't involve the full Satake sheaf. So you kind of T mu contains this shift by d and Tate twist by d and a half, and you first undo it over here. But that's why it shows up here. It shows up because of geometric Satake. Okay, and what I want to do now is give you an idea of how to prove this theorem by just drawing a big diagram.
Sorry, Anna, was it so the Weil group action is coming from the div1 factor, is that right?
Yes, that's right. The Weil group action comes from the div1 factor. Precisely. I should have written this, that, okay, T mu of G is this, but you should really think of this as some object in d bun G lambda, but in some sense equipped some kind of WE equivariant object. And that's because local systems on div1 are essentially representations of the Weil group. That's exactly
Maybe
right.
you could use a third board instead of erasing this one.
There is one more board. Oh, great, thank you.
Is it also Galois of A, or can you replace W by Galois of A or not?
Sorry, just a second. There is something. So the question was what? Sorry.
Whether the Galois group of A instead of the Weil group works also in this discussion or not?
No, you should use the Weil group, because somehow in the work of Fargues and Schulze, the Weil group is the one that shows up naturally because of this mirror curve div1. This is okay. All right. So the idea of the proof for this theorem. All right. So I'm going to draw the Igusa stack diagram, but I'm going to, well, if you remember from Mingjia's talk, when she defined the map from the Shimura variety to the Igusa stack, she forgot everything at p. And so that means really you could take a quotient by GQP and you'd still have an Igusa stack diagram. So there's a stacky diagram where I take a quotient by GQP on the top row. Okay. And it's still, I guess, a version of the, let me just abuse notation and still call this BL. To Bunji, and then the Igusa stack. All right, and so this is pi bar Hodge Tate. And then there's a map to just the classifying stack of GQP. And this map I'll maybe call Q. Right, and then I have, so this is a Cartesian diagram over here. And maybe I'll call this the Cartesian diagram 1. But then there's a second Cartesian diagram. So remember that this includes into bun G via I1. And then over here, turns out, so this includes into the Hecke stack for G. What did I call it? Just Hecke mu. Okay, but still for the group G. So here, poles are bounded by mu inverse. So maybe what you need to do is switch the order. So this is a kind of a modification of the trivial G bundle with poles bounded by mu inverse. If you switch the order of the bundles in the modification, you get modification of G bundles with poles bounded by mu. And it exactly lies over the neutral point because we're modifying the trivial G bundle when we look here. And so it turns out this is also a Cartesian diagram. Maybe I'll call this Cartesian diagram 2. Okay, and some other thing that I should tell you. So this one is an open immersion. So in particular, open immersions are smooth. In this world of p-adic geometry, you can say they're L-cohomologically smooth, notion introduced by Schulze. And this map, it turns out one can also prove that this map is L-cohomologically smooth. So usual notion of smoothness doesn't make sense because you don't have differentials in this world. But there is a notion called L-cohomologically smooth, and for which one can prove smooth base change. Okay, so now essentially what you want to do is you want to compute the total cohomology as a GQP representation. Turns out that means you need to take the push forward all the way along this composition. Okay, and you want to do some base changes. So you can imagine just pulling back the constant sheaf and pushing forward. You're going to do base change along the first diagram. You can do L-cohomologically smooth base change. Take this push forward and take this pull back, and then continue pushing forward. So let me write down this step. Right. So this is the same as RQ star BL upper star, and then you end up taking the relative cohomology of the Igusa stack. So that's the sheaf that I called F. And this uses smooth base change for diagram 1. Or you could, in this case, this is proper, so you could do proper base change instead for this morphism. But that's the argument that will generalize also when you don't know that this morphism is proper. All right. And now we need to use base change for this other diagram. And I need you to squint a little bit. So let's see. This one is basically PR2. I mean, I could add a div1 factor here if you wanted. And then PR1 is over here. And so when you're pulling back along this map, well, you could imagine pulling back along this map and then along this open immersion. And then you're taking a push forward here. So instead, what you could do is pull back like this, push forward like this, and then take pull back. And so that's exactly I1 upper star of T mu, except this is not quite. So pull back and push forward is not quite the Hecke operator because I haven't taken a tensor product with the Satake sheaf. So if I undo the tensor product with the Satake sheaf, which I can actually do in this case because it's just this shift and twist, then that's what I get. So it's really F with this minus D and minus D over 2. Okay, so this is the idea of the proof of the theorem. And I should say that the Hecke equivariance away from P and the equivariance with respect to the inertia subgroup of E is pretty obvious from the diagram. And then you have to be a bit more careful to show that you really have equivariance with respect to the full V group. And this comes from really thinking about the top of the Igusa stack diagram as having a Weil descent datum and keeping track of that as you do this argument. Okay, and now I can mention some applications. And so there's a lot of applications. I'm going to first kind of try and survey, but if I forget something, either let me know or, keep in mind there may be things I just don't know about. And then I want to give you a sketch of proof for 2 of those applications. So that's the plan. Sorry, I went ahead of myself. I can do one more thing before I do that. I think I was too excited to. So one can go even a little bit further. So this has really only been on the geometric or the automorphic side of categorical local Langlands. Right? So I've just stayed on kind of sheaves on Ban-G or smooth representations of GQP. But in fact, one can even rewrite this formula using the spectral action of Fargues and Schulze. So that's the other thing, is that, so we can rewrite the formula using the spectral action. Right, so this connects the spectral side to the geometric side, or to the automorphic side. So I'm going to take the moduli stack of L parameters. And maybe I'll call this, I don't know, I could call it XLG or XG, or people have various preferred notations. And just to kind of compare it to the notation used in the work of Fargues-Schulze, one can think of this as kind of some moduli of continuous co-cycles of the Weil group valued in the Langlands dual group of G. And actually defining this continuity in full generality is subtle. It uses condensed continuous in the sense of condensed mathematics, and then up to G hat conjugacy. All right, so this is a moduli stack of LG. And let me do one more thing, which is base change this to lambda, my ring of coefficients. LG valued L parameters. This representation of the L group that I denoted by V mu, well, it gives you a vector bundle on the classifying stack of G hat. And if you pull that back to this moduli stack, you get a WE equivariant vector bundle on the moduli stack of L parameters. XLG, sorry. Under, pull back along. There's a natural map from this to the classifying stack of G hat. Okay, and so the Weil group action comes from the Weil group action, or the restriction of the Weil group action on the universal L parameter that lives over this moduli stack. And you have to be maybe a bit careful when the group is non-split to see that you really get a WE equivariant vector bundle here, but you do. Okay, and I'm going to call this vector bundle curly V mu. And then what Fargues and Schulze tell you is that, well, the geometric action of the Hecke operator, T mu, on d Ban-G lambda can be expressed as the spectral action of the vector bundle V mu.
Excuse me, so this curly V mu is different from the product of V mu, but you do something else, or
No, I just take the pullback, but then I observe that it's equipped with, it's equivariant for this WE action.
Okay. When G is split, is this trivial action?
No, it comes from the universal. So there's a, so let's say G was like GL2 or something, or GLN, right? There's some universal object on this moduli stack of L parameters. And there's already a Weygroup action on that. That's the universal action. And so that would be the action in that case.
But if you just pull back, how is it to do with the universal?
You just think through what pullback does, and you're going to see that this works.
Okay. So the representation of GL that you take is with which coefficients? Is it lambda coefficient?
Yes. That's right.
And so mu is the highest weight or something like this?
Yes, mu is the highest weight.
But the theoretically reducible representation of algebraic groups works well in characteristic 0. In general, you have different, like which representation, I mean.
So, I mean, I think I can assume that L is good for G in some sense, and then there's a well defined theory that Fargues and Schulze used. So maybe for a general group G, I might need to throw away finitely many primes.
And probably also since it's minuscule, so you're just seeing the like W orbit of mu, there's probably no room to really have a difference anyway.
Okay.
I think you want to take the standard ones, but correspond to street functors on the just attack the side.
All right, so the action of T mu on D Bungie lambda corresponds to the spectral action of V mu. And then, so we rewrite our formula over E bar as I1 upper star of V mu acting on this sheaf, the relative cohomology of the Igusa stack with this shift and twist. So this is the spectral action constructed by Fargues and Schulze. Okay, and it turns out that this is very useful for computations, and you're going to see this in practice, well, in a few minutes, but especially also in Mingjia's talk that's following this one. So as a corollary, I can express the cohomology of the Shimura variety at some finite level as following. So now I take some finite level at P as well. And so that means I'm taking invariance, Kp invariance of this whole thing. And so you can think of this as an R-home from the trivial representation of Kp into this. And then using Frobenius reciprocity for compact induction, you can think of this as an R-home that's GQP equivariant from the compact induction from Kp to GQP of the trivial representation into I1 upper star of this whole thing. And then using the adjunction between I1 lower shriek and I1 upper shriek, where I1 upper shriek is the same as I1 upper star because I1 is an open immersion, I can write this as an R hom in this category D Bungie lambda of I1 lower shriek, compact induction, GQP, sorry, Kp to GQP of the trivial, and into just V mu acting on F minus D over 2. Okay, so you can express the cohomology of the Shimura variety at any finite level Kp as kind of taking this sheaf, so the Igusa sheaf with some shift and some twist, and then, well, on the spectral side, it would be tensored with a vector bundle. And then you probe it with this I1 lower shriek of this induction. And so under categorical local Langlands, for instance, when, say, if my group is unramified and Kp is the hyperspecial maximal compact subgroup, then under categorical local Langlands, this induction should correspond to the structure sheaf of the unramified locus. Or if I take Kp to be an Iwahori subgroup, the Iwahori also in that setting, then this would correspond to the coherent Springer sheaf. Right? So this, when Kp is hyperspecial, corresponds to the structure sheaf of the unramified locus on XLG, I guess. And Kp is Iwahori. This is known as the coherent Springer sheaf. So this is just to say that there's really a lot of explicit computations that you can do for the cohomology of Shimura variety using this formula over here and then passing to the spectral side under categorical local Langlands. Of course, this is conjectural in the setting of Fargues-Schulze for now, but still, there are a lot of computations one can do. And also morally, this is the kind of argument used in recent work of Yang and Xinwen Zhu, say to prove results about the cohomology of the Shimura variety. All right. So now I can state some applications, and I can discuss, hopefully, 2 of them. And so I don't have much time, but somehow the whole point of doing this was to say, and now all these applications become very kind of conceptual and very easy to explain. All right, so first I'm just going to mention various applications. So one is to torsion vanishing in the setting of Shimura varieties. So this roughly says, well, maybe let me not even write it. Let's see. Maybe in the generic case. Right, so for some sufficiently generic system of Hecke eigenvalues, or some sufficiently generic system of Hecke eigenvalues at P, the cohomology of the Shimura variety is concentrated in the middle degree, and this works with torsion coefficients as well as with characteristic zero coefficients. And so there was a lot of work about this, say, over the past decade. And so Schulze and I proved a very preliminary version of this theorem, but still using the cohomology of the Igusa varieties. So that's why I mention it. It's really more of a precursor, because we looked at Igusa varieties. There was no Igusa stack, and we didn't really use geometric methods. But then Koshikawa proved a stronger version of our theorem using geometric methods, so using the work of Fargues and Schulze, but still without the Igusa stack. And then Hamann and Lee, I guess, well, they proved a stronger version than Koshikawa's theorem. They also used the work of Fargues and Schulze, but they also, in some sense, at least morally, their argument makes the most sense or is simplest to understand using the Igusa stack and using this theorem. That's maybe, is it still on the board? No. But using this description as the Hecke operator applied to the relative cohomology of the Igusa stack. So maybe, you know, the Igusa stack isn't strictly necessary for what they do, and one can still work with kind of the Newton stratification, but the Igusa stack definitely makes what they do a lot more conceptual. And then morally, there's recent work of Yang and Zhu, where, you know, they don't literally use the same setup, but morally, they use kind of the same formula. Okay, so that's one application. Another application is Eichler-Shimura relations. And hopefully I'll get to talk about this. So say you look at an unramified prime, the cohomology of the Shimura variety, any lift of Frobenius has to satisfy a particular Hecke polynomial. Right, so this is something conjectured by Blasius and Rogowski maybe 30 years ago. And there has been work on Eichler-Shimura relations since then, and there's been a lot of progress using different methods. But the Igusa stack and this formula that I wrote down for the cohomology of the Shimura variety give you, again, a very conceptual way of looking at it. And this is, maybe, let's see who I should mention here. Maybe I should say there's a, Koshikawa did this for local Shimura varieties. And then this inspired the work of Daniels-van-Hoften-Kim and Zhang for global Shimura varieties. And so as I said, there's other work, maybe I should say, work here of Lee and Wu using other methods. And Lee actually proves it on the level of algebraic cycles. Wu uses a kind of excursion operators and an S equals T theorem. But then there's also these approaches that really use something very close in spirit to the formula I wrote down. There's Ihara's lemma, which is, I guess, a conjecture in higher dimensions formulated by Clausel, Harris, and Taylor more than 20 years ago. And under some assumptions that are not too bad, Yang proved this, and he exactly uses this kind of formula for hyperspecial and for Iwahori level and computing on the spectral side and various levels in between. So this is again morally because he works in Zhu's setup. And then maybe some other applications that are work in progress, so not available yet, to kind of geometric Jacquet Langlands in the sense of Xiao and Zhu, and also applications to the actual Jacquet Langlands correspondence. So that's where the cohomological formula comes in. This is work of Van Hoften and Sempliner in progress. And there's applications to the local plectic conjecture of Nekovar and Scholl. It's a local version, because we've base changed to QP to access the Igusa stack. And this is work in progress of Feng, Tamiotso, and Zhang. Maybe you've seen Mingjia give a talk about this. Okay, so the upshot should be that there's a lot of exciting stuff happening in understanding the cohomology of Shimura varieties and kind of using the Igusa stack diagram and the cohomological formula.
And what's the plectic group inside?
I mean, I think it's just like you kind of, it's the QP version of it, but I suggest you just ask Mingjia about it. I'm running out of time, so maybe I'll leave that since that wasn't something I was planning to discuss. And so what I want to do is tell you about torsion-vanishing and tell you about Eichler-Shimura relations in my remaining time. I think that clock is tricking me, so I do have 10 minutes. Okay, right, and I'm not going to try and define generic, so it is what you want it to be, like, I don't know, Langlands-Shahidi type, or, yeah, let's not worry about that. But let me say that there is a perverse T structure on d1g lambda that is morally obtained by gluing the standard T structures on the individual Newton strata in Bungie, right? So one stratum looks like the classifying stack for this GB tilde. And so I have these two standard T structures where the shift is by this dB, which is, I mean, in some sense, it's the dimension of this GB tilde in the sense of GB tilde is L cohomologically smooth, and there's some, you know, dualizing sheaf, and you can describe it using this shift. It's also more classically the dimension of the corresponding Igusa variety, say considered as a perfect scheme over FP bar. Okay, and it turns out that these conditions on each Newton stratum give you a T structure on d Bungie lambda. And now you can prove torsion vanishing using two ideas. And so one idea is that F, which is the relative cohomology of the Igusa sheaf, is, well, okay, so technically it's something called ULA in the work of Fargues and Schulze. And I mean, it's a technical condition, but it roughly means that its stalks at individual B's have admissible cohomology. And it's something that guarantees that this sheaf is at least reflexive under Verdier duality. But then because we're in the compact case, so it's needed so that you make sure kind of the 6 functors interact well with Verdier duality. And then you can prove that it's actually even Verdier self-dual. And that's where I'm using the compactness assumption. And then you can prove using this that it is a perverse sheaf. Okay, and in talk 4, I can explain a version of this argument that works for some intersection cohomology version of this on a non-compact Shimura variety. But I'll just say then the perversity comes from the computation of the stalks are just the cohomology of the Igusa varieties. And the Igusa varieties are affine, and so you get the right bound using torsion-vanishing. Okay, so this is not just any random sheaf on d Bungie lambda, but it's actually a perverse sheaf. And the second idea is purely local. And so this goes back to work of Hamann on geometric Eisenstein series, but in the purely local setting of kind of studying Hecke operators on d Bungie lambda.
Excuse me, when you say F is ULA, is it ULA over what?
So it's a ULA sheaf on Bungie with respect to the map to a point. Okay, so the second idea is that if phi p is some kind of generic L parameter for some sufficiently good notion of this genericity for G, then you can essentially see the localization of F at this parameter inside here. And moreover, there's a localized Hecke operator that acts on it that will give you kind of the localized cohomology of the Shimura variety. And this kind of localized Hecke operator is perverse T exact. And so you have a perverse sheaf. You shift it so that it's in degree D. You apply this Hecke operator that's perverse T exact. You get a smooth representation of GQP. But there, the T structure is just the usual one. And so using perverse T exactness, you get that the cohomology of the Shimura variety after localization at this generic parameter is concentrated in the middle degree. All right, and I should write, so this is something that Hamann and Lee prove, but using this purely local work of Hamann. Sorry, you shouldn't get. Right, so using the theory of geometric Eisenstein series in this setting of Fargues and Schulze. And somehow only for kind of the torus, but that's good enough for these generic parameters. All right, and I also want to tell you about Eichler-Shimura relations. Partly this was my assignment from Mingjia, was to cover these two. So I'm assuming that G is unramified and that KP is hyperspecial. Just to state roughly what you're supposed to prove. So you look at the cohomology of the Shimura variety with finite level at P. And this has an action of the spherical Hecke algebra at P. And it has an action of the Weil group. But really, the action of inertia is trivial because we're at an, level is prime to P. So this is trivial. And then you take sigma to be any lift of Frobenius. And then the claim is that for this kind of using this action, you can look at kind of h mu of sigma and show that this is 0, where h mu is some Hecke polynomial. So it's just some polynomial with coefficients in the spherical Hecke algebra in one variable. Let me say this. And it's determined by the Hodge co-character. And so, for example, in the case when G is GL2, the global group is GL2, you have that this h mu of x is just x squared minus tpx plus p sp, where this is the double coset operator for p001, and this is the double coset operator for p00p, right? And the arithmetic Frobenius on cohomology famously satisfies this polynomial. And so Blasius and Rogowski conjectured this more than 30 years ago, that this holds true more generally. Okay, and so using ideas of Koshikawa in the local case, and also Drinfeld and Xiao-Zhu, these four authors, Daniels-van-Hoften-Kim and Zhang, gave a proof of these Eichler-Shimura relations for Shimura varieties of Hodge type, and even they were able to do it by going even to Iwahori level, where you can also formulate something. So the idea of proof, so it's in this paper, but it also relies on, let me at least say Koshikawa, because I think that's kind of the closest, is to compute on the spectral side, basically. So one is that there is a Weil group action on endomorphisms on this stack of this vector bundle V mu, and then using the formula for the cohomology of the Shimura variety, this gives you a Weil group action on the cohomology, say at infinite level, right? So this uses the theorem that I sketched earlier in this talk, but this agrees with the usual WE, like the geometric one that you see on the cohomology of the Shimura variety. That's part of this WE equivariance. And two is that similarly, there's a way to see the Hecke action as endomorphisms here. So you take something called the spectral Bernstein center, which is just the ring of regular functions on the coarse moduli space attached to the stack XLG. And this, on one hand, has a map to the usual Bernstein center, which is Z of GQP with coefficients in lambda. So this is usual Bernstein center. Right, which maps to endomorphisms of the Shimura variety. But also, this also maps to endomorphisms in X, LG, V mu, which again maps here. So the claim is just that this diagram commutes. And then you can essentially kind of prove the necessary relation in here, so on the spectral side, and where it reduces to Cayley-Hamilton relations. So I'll just say that the Eichler-Shimura reduces to Cayley-Hamilton on this side, on the spectral side. Right, so it's just justification that this formula is very powerful. Maybe I'll just say somehow the one thing that 3 and 4 have in common is they're both particularly hard to prove when G is not split over QP. And there it's not easy to tell apart the different Newton strata. And somehow this formula and the work of Fargues-Schulze and somehow subsequent developments really make it possible to handle those cases. All right, thanks for your attention.
More questions?
So the Igusa variety there, which is affine, is it an algebraic variety or a rigid variety?
It's an algebraic variety. It's just it's an inverse limit of algebraic variety, of finite type varieties over FP bar. So it's as nice as you could.
Okay.
Is this H mu? Is this the characteristic polynomial? Do they prove it's the characteristic?
No, they do not prove that. It's just that it's satisfied. Yeah. They prove that Frobenius satisfies this polynomial, not necessarily that this is, Sorry? Maybe I get confused between characteristic and minimal. It's not the minimal polynomial that the Frobenius satisfies. Sorry? Yeah, you could have multiplicities, exactly.
Okay, well, thank you very much.
Thank you.